I have some pulleys, I have some string, I have some masses. So let's see what we can do. You back on and see if I can find two masses that are relatively close. 5.62, 5.1, that's 5.7. You do it. Perfect. Let's do those. 500.52, 500.62. Cool. Let's do this. Cool. So pulleys, I like pulleys. Pulleys are an important thing. Okay, cool. Consider two equal masses hanging from a pulley. Here they are. What's the point of a pulley? Anyone to pull? It's in the name. What's the point of a pulley? Yeah, if I have a collection of pulleys, I can make things easier to make masses move up and down. It's at its most fundamental level, though, that is not exclusively what the pulley is for. Anyone know what the pulley is for? Let's say if I wanted to move one of these masses. If I just had this guy, forget this guy for a second. If I wanted to move this guy up, what would I have to do? Ignore the pulley. Pretend the pulley's not here. There's no man behind the curtain. I want that guy to go up. What do I have to do? Forget the pulley. I have to pull. I have to pull. I lift. The pulley lets you redirect the force. It says, if I want to lift this guy, I don't have to anymore. Because by running a string up and over a pulley and then attaching another mass to it, if I want this guy to raise, I can do way less work. Gravity is pulling down on this. Gravity is also pulling down on this. But what the pulley allows me to do is the pulley allows me to redirect the downward force on this mass. Right? Because if I pull down on this, it's going to pull down on this string. But by going up and over the pulley, what's that going to do to this side of the string? It's going to raise it. So the purpose of the pulley is just to redirect a force, which is an important thing to recognize. If I let go of the pulley right now, what's going to happen? It's going to fall. Why? He said it's going to fall. You said because they both ways the same. They do both ways the same. I grabbed two masses. One of these masses, I don't remember which is which. One of them weighs 500.62 grams. The other one weighs 500.52 grams. So the difference in these masses is 1/10 of a gram, or 1/10,000th of a kilogram. Well, I've managed to find ones that were pretty close together. You're saying, someone over here, I don't know, I keep pointing at David. I don't know if it was your voice or it was a disembodied voice from this table. Was it you, David? Yeah. Said they should move. You're suggesting they should move because the masses are the same. Now you know, because I'm redrawing it up. Does anyone else have any gut feelings about this? Do you think they should become equal? Why? Same reason I said that because masses are the same. Your gut says that they should level off. Or I'm just holding it to hold it. Just to throw you off the It's the theatrics of physics teaching. Am I doing something here to prevent something from happening, or am I doing something, now this is actually nothing. Or am I doing something or am I doing nothing? I'm effectively doing nothing. So let's talk about this. What's the free body diagram going on here? What forces are acting on these masses? Gravity. Well, that's what's acting on this one. Gravity downwards. This guy, gravity downwards. This guy also has tension acting up. This guy also has tension acting up. What can you tell me about these two tensions? They're equal. It's the same string. I haven't changed the string anywhere in between. It's one. If you don't believe me, I mean, your REM helped me cut it. You can vouch for me. Yes, it's the same string all the way through. Unless you want to totally undermine me. No, it's not the same string, guys, the REM says. So, if these masses are effectively equal, 1/10,000th of a gram difference, what can you tell me about the force of gravity on this one versus the force of gravity on this one? It should be darn near equal. Force of gravity is mass times 9.8. So if these two forces are equal, should this thing move? We're ignoring things like the mass on the string. This was obviously more string here. But Irem showed up, last week we had this conversation. The string, well, maybe it was Kai. The string is effectively massless compared to everything else that's going on here. If I let this thing go, should it move? If all of our assumptions are true. Okay, so let's see. My finger's out of the way. Is the thing moving? I was scared because I've never actually done this before in person. I was like, it's going to move. It's not moving. The forces here are equal. There's no reason why. I mean, I could balance them. But it shouldn't, because the forces downwards on these two pulleys are equal, it shouldn't matter where, again, assuming we can ignore the mass of the string, it shouldn't matter where I place them. It's not a balance beam. Like a balance, a measuring scale would level them, right? It's not one of those. It shouldn't matter where I place. If we can ignore the mass on the string, these should be equal. So that's all a pulley does. All a pulley does is it redirects a force. Both of these forces are downwards, but because of the presence of a pulley, this upward force here and this downward force here, we can equate. Yeah. I did. Nothing. No thumb here, nothing. Nothing. Effectively nothing. So the purpose of a pulley is to redirect things, and if that's true, then to help us analyze these things, we can just redraw this as if the pulley wasn't there. Pens, and here we go. Again, we're going to make some notes up here. When we're talking about pulleys, we're going to ignore the mass of the rope. We're going to ignore the friction in the pulley. At this stage, we have to. And I'm hoping with what I just demonstrated that was, if not sufficient to convince you, then at least sufficient to make you doubt your own understanding so that you're more amiable to how I want you to see things. Because the pulley just redirects things, what I could do, one way to tackle problems like this is just to take these masses. I'll demonstrate for you what I'm about to draw. What I could do, I'll use to hold this. Instead of leaving it like this when we analyze the problem, I could just, now that we've analyzed the problem, I say, okay, this is what's going on. I know I've got forces of gravity acting down here. To make it easier to actually process on the page, I can just take this and say, okay, freezing it in place, knowing I've got gravity acting downwards, I can just pick it up and say, okay, I'm going to redraw it like this, ignoring the pulley in the middle. I'm just going to redraw it. I'm going to assume that it was the same as what it was before. I have a force of gravity acting that way off this one, that way off this one, because that's effectively all the pulley has done. So one way to analyze these problems is to pull it off the pulley once we've established what's what, and then figure out which way this is going to go. So what you guys said was that this guy down here has a force of gravity. This guy down here also has a force of gravity. This guy has a tension here up, and this guy has a tension here up. To simplify how we view this problem, one of the things you can do is to just pick it up and pull it off the pulley once you've drawn this free body diagram. Okay, well, let's change it. Let's say now instead the two masses are just hanging free. That one's that one. This one's this one. The pulley is no longer involved. The string goes between them, and I'm going to draw my forces the same way. This guy, having been picked up off the pulley, is going to have an FG this way. And the tension's going to be back this way. This guy's going to have a tension this way. And when it was sitting on the pulley, this guy had an FG this way. Because I've got a bunch of forces acting in multiple directions, I need to include a direction I want to call positive. You guys seem to like to the right being positive, so let's just continue to do that. And now this is a way, again, an option for analyzing these things if we struggle to visualize it on the pulley. I don't love doing it this way, but it is a method you can use if you would like, because that's all a pulley is doing. It's redirecting things. And this is where things get confusing for students with the pulley. If I said to the right was positive here, how can I talk about directions on this side? What is to the right in this diagram? What is its equivalent over here? Sorry? Down. If down is positive, that means both of these have to be positive, and these two forces are these two forces. And on this diagram, they act in opposite directions. So, well, how do we take? That's a great guess, and that's exactly what the problem is. The struggle that students have with pulleys is, what do I do with the pulley and what I want to call a positive direction? Because if I call down positive, it means both of these are positive, both of these are negative. It means these two won't cancel, and we know they should. So what do I do? That was a great first guess. Brad. What do you mean one half's positive and the other half's negative? Like you just want to call both of these positive and both of these negative?
Well, both FGs are the FGs are positive and negative, and the tension is the other way around.
That's the same thing Ray Reed suggested. Emma. That's the same thing these two just suggested. Yeah, that's the same thing. They both said it slightly different than you did, but all three of you said the exact same thing. What you're suggesting is taking... But why not? Okay, so if this isn't gone, you're cool saying all to the right is positive here. But your positive and negativeness needs to be tied to a direction, not to the forces acting. So if you're going to call left or right, if you're going to call right positive, you've got to call right positive for everything acting to the right. That means if we don't have a pulley, forget the pulley. It's one of these kinds of problems. And you guys had no issue with this last week. You said, okay, to the right is positive. That means that this 40 Newton force had to be positive. This tension was positive.
That one was negative because it's acting in the other direction. We had the same thing down here with friction. We said that these two were negative, these two were positive, and it allowed us to solve for the acceleration due to gravity and the tension in the string. How do we handle this here? Brad?
So the FG on the M on the right and the FT on the block on the left are both acting right, so both of those would be positive, and then the FT facing left and the FG facing left would be negative?
Yes.
Okay.
Now let's see if everyone can picture what you just said. Here's what he just said.
Okay, let's go over here. Here's functionally where we're at. Having taken the pulley out of the picture, it's lying flat, you guys can't see it. We said that this thing has a force of gravity acting that way, there's a tension here acting that way, there's a tension here acting that way, and then there's a force of gravity coming off the bottom of this, going that way. We said, I want to grab something I can use here that has some bend to it. It's really big. Ooh, let's grab a rubber band. Oh, let's grab a bigger rubber band. Let's cut the rubber band. Hey, Mr. Morrison, what do you got going on?
How much I need my scale?
It's that one right in the middle there. Thank you, sir. Is there a convenient time I can borrow it back? Oh, actually, I don't need it anymore. Never mind. Okay. Here's the direction we call positive. I just cut it onto the rubber band. The rubber band's going to be nice. I'm going to place it here too. It's pointing that way, in case anyone's confused. What Brad was suggesting was that if we called to the right positive, that means the force of gravity coming off the butt end of this guy and the tension going this way both need to be positive, and the tension going that way and the force of gravity coming off that way also need to be negative. But what does that do when we go back to the pulley on the right? How would you describe what you're trying to describe if we go back to this situation here? What if I pull a little back on the pulley? What's it going to do?
If you put it back on like if you hang the pulley.
Yeah, it's hanging again. What's that going to do to this arrow that I've now created?
Well, it's gonna make it like them like near each other, right? So that they're like balanced. Because like if they were all acting like the same way, then they'll make it like flip over, right? Like it would make it all go to one side, so it becomes balanced. So they're like equal and opposite.
So how do I draw the direction that I'm going to call positive on that pulley, Emma?
So that's equal
In this case, because the masses are equal, they would have to be. So here's what I'm getting at. If I pick this pulley back up, let's feed this through the pulley. Okay. If anyone's confused about what I'm demonstrating, get up, come take a look at what I've done. If you want to see it, come take a look at it. I'll leave it there for a second. Nobody wants to see it, nobody wants to get up. Okay, cool, let's demonstrate this then. If I take this thing, the pulley, and I pick it back up, what is happening now to the direction I called positive before? The direction itself also hangs over the pulley. Lying on the table, we said to the right towards these guys was positive. But now, what's the arrow doing? It's going up over the pulley this way. Let's see what I'm trying to demonstrate. See what I'm trying to demonstrate? What I'm trying to demonstrate? So when you've got it drawn flat, it's easy to say, okay, I'm in one dimension, I'm just acting left, right. But when I've got a pulley system, what you need to do is the direction that you call positive also needs to drape itself back over the pulley the same way we've done here.
So what we call to the right here would functionally actually be this way. And that we would say up over the pulley clockwise is the direction I'm going to call positive. So that means that on this side of the pulley, up is positive, down is negative. And then on this side of the pulley, following the arrow, it means that this guy here would be negative. So this is negative, this is positive, this is negative. It makes this guy down here positive too. Which is what Brad was trying to verbalize, and he's right. But unless you're picturing the same thing he is, it's hard to understand sometimes. So, the direction you choose here or here doesn't actually matter. You could say, we could have said to the left. If to the left was positive, how would this have changed? Instead of going clockwise, it would have gone counterclockwise. It's totally arbitrary. So let's do an example. Do that here. Hello. What is going on here? Now these masses aren't equal. I don't have a 500 and a 500. This is what I've got. I've got this guy. This guy. Brad, are you harassing people? Hey, Reed, are you harassing people? You're getting harassed by people. Okay. So now, I don't have equal masses hanging from a pulley. Okay, this is what we had to start. This is what we've got now. Would you be so kind as to hang that on the bottom of that? Oh, hold on. Sorry, I screwed it up. Okay, hang that guy on the bottom. The other one then. Let's try better. Okay, now what do you expect to happen now? Here's the pulley system. What do you expect? That would make sense, right? You have no reason to be on your phone, get off your phone. Is that a hand? Okay. I mean, we all expect the same thing, right? This side is heavier. My right, your left is heavier. We expect this thing to drop as soon as it is kind of, I'm struggling to hold it with my finger. If I pull this up, it's going to slam back down. So, let's analyze the problem. How did they accelerate? It's important to recognize that as one accelerated down, the others accelerated up at the same rate. They're still just like what we did last Friday. They're still moving together. It's still one system. So that part of the problem hasn't changed. So we've got a situation that looks like this. We've got a 6 kilogram mass on the left. We've got a 4 kilogram mass on the right. Let's draw the free body diagram, and then we can pull it off and analyze it. What's the free body diagram here? What forces are acting on the 6 kilogram block? Brad. Gravity down, tension up, and now we can actually start putting values here. I don't know what tension is, but Fg we can find. Fg is always going to be the mass of the object times the acceleration due to gravity. In this case, 6 times 9.8 is 58.8. What are the forces acting on this guy? Yeah, there's a gravity. Gravity's down on this guy. We can find the value for that too. It's going to be 4 times 9.8, which is going to be 39.2. I can zoom this in, make it a little bit easier to see what's going on. What other force is acting on the 4 kilogram mass? Ft. There's a tension. And what can you tell me about these two FTs? What can you tell me about, well, I mean, we got two different gravities here. So they have to be equal to each other. These two have to be equal to each other because it's the same string acting over the pulley. These two tensions have to be equal. If they're not, it's not a doable problem at this stage. So if we're going to label a positive direction here, which way would we call positive? Which way makes the most sense? Sorry? Well, I mean, if we, okay, hold on.
Okay, so like FG on the core block being positive kind of thing?
Why do you want that one to be positive?
That's actually right.
It's to the right of what's you, but does that make sense? Let's for a second pick this thing up and place it down and out. Did you have a thought before I do that? This guy, you want this guy to be positive? You want this guy to be positive. You want the right FT to be positive because you're suggesting that this block is going to go up. Why is this block going to rise? Because this block is heavier, this block should drop, this block should rise. You want this one to be positive. So if this one's positive, then what's positive over here? This guy needs to be positive. So Emma's suggesting that because the system's going to go this way, she wants this guy to be positive and this guy to be positive as well. That's how I would do it. You don't have to. It will work out either way. But then you're introducing a negative that you need to make sure you address. If that's how you want it, Emma, if you want this guy to be positive and this guy to be negative, you need positive to go up this way and down this way over the pulley. So if you're giving me a direction on the pulley, the direction here is going to be counterclockwise. Counterclockwise. Which for all of my grade 10s who don't know how to read a clock, it's a totally pointless description. So if we wanted to, again, if it helps you to visualize it, pick it up, take it off, slap it down on here without the pulley, it would look like this. You'd have this guy, they're attached here in the middle. You're redirecting these forces now, so the FG is not down, the FGs would be to the left and the right, because this is the 4, and this is the 6. So this would be the FG here, the 39.2. This is going to be this FT. This is going to be this FT, that guy right there. And then the FG coming down off the 6 is going to go to the left here. FG equals 58.8. For some of you, you might not pick a positive direction until you've actually drawn this. If you draw it here, it's easy to see, okay, this one's bigger than this one. The whole system's going to slide this way. So let's call to the left positive. But for those of you who like to work on the pulley, you're going to say, okay, well, left positive here means counterclockwise on the pulley itself. I don't care if you do this drawing. If it helps you understand things, by all means. But there are limitations to everything we do here. There's limitations to keeping it on the pulley, because now you got to think in 2 dimensions. If there's limitations here, because if you draw this without drawing the proper free body diagram, the mistakes that I see students make is that these 2 forces of gravity, they draw this way, which isn't the point. The point of the pulley is to draw them left, right. Either way, however you choose to demonstrate it, now we've got a system with all of our forces, our directions, and now we can actually go ahead and find how these things are going to accelerate. I've got everything in this chapter starts with F net equals ma. And now I can go ahead and I can start plugging all my forces into this F net equation. The way I would continue to recommend you do this is whatever direction you called positive, start at the most positive edge and work your way backwards. So if you're using this diagram, you're going to start here and you're going to work this way. If you're using this diagram, you're going to start here and you're going to work up and over the pulley. Whichever one you use, this FG comes first. So we're going to have the, let's call this block 1 and this block 2, which makes this block 1 and this block 2. So I'm going to have the Fg acting on block 1. That's this guy. This force is in the opposite direction, so I'm going to have Ft. I don't need to label this thing special because these two Ft's are equal. So Fg1 minus Ft. As I follow the string, I've got a positive force, positive Ft, minus Fg on block 2 equals, now I want this mass to be the total, because again, the system accelerates together. I'm hoping I was sufficiently able to convince you of this. M total times the acceleration, which is what we're looking for. So now we can start plugging things in. 58.8, these two tensions are going to cancel. They're equal and they're opposite. Minus 39.2 equals 6 plus 4 times A. So if I go ahead and subtract these things, 58.8 minus 39.2 is going to be 19.6 equals 10A. Divide both sides by 10, and I'm going to get that the acceleration of the system is 1.96 meters per second squared. Counterclockwise. Comments, questions, concerns about what I've done there? I'll give you a second to write that down. The math isn't any different from what we did on Friday. So if you were away on Friday, you're getting a reintroduction to everything you would have missed on Friday. The only weirdness here is the directional change of the pulley. So now, if there are no questions, we can go ahead and we can find the tension in the string. We're going to do that the exact same way we did it on Friday. To find the tension in the string, what do? When you have a system like this, and we found the acceleration of the entire system, it means every object in the system is going to accelerate the same way. So to find tension, what do? What did we do on Friday? Yeah, you pick one block to work with. So, Raina, pick a block. There is a easier block to pick, but I tried to convince you on Friday that it doesn't actually matter. If you're careful, you'll get the same value either way, but there is one block that is going to be easier to work with. You got a 50-50 shot if you're just guessing which block's going to be the easier one to work with, block 1 or block 2. Why? Okay, what are we looking for? The tension. And on block 1, the tension is positive or negative? It's negative. So what's the easier block to pick? Block 2. If you keep the thing you're looking for as a positive value, you're not going to introduce a minus sign. And I know you guys are in grade 11. Your math skills are strong. Minus signs shouldn't trip you up, but they do all of the time. I used to teach at U of V. I'm teaching first-year university students. Minus signs still stuck them too. If you can avoid introducing an unnecessary minus sign, don't do it. So I'm going to pick the second block. If we do that, we're going to isolate the 4 kg block. If we do that, I can cover it up on this picture or on this picture. I'm going to write down my F net equation just for that block. So we're going to have F net equals MA. On the 4 kilogram block, I've got Ft positive, Fg negative. So I'm going to have Ft minus Fg equals MA, and now I can plug everything in. Ft minus 39.2 equals 4 times 1.96. Now, all I have to do is multiply these two things together, And because I'm subtracting the 39.2 on the left-hand side, to isolate for FT, I'm just going to add it over to the other side. I'm going to add that guy over there. And I'm going to find, if I had more space, put it right here, FT is going to equal 47.04 newtons. And it doesn't matter which block you isolate. If you put it over here, it would be negative. If you put it over here, it's going to be positive. It doesn't actually matter. Questions, comments, concerns about pulleys? Cool, then let's make it more interesting. Let's forget the pulley for a second. And we're going to throw the thing on the table. So now we're going to forget pulleys, and here's what we're going to do. We're not going to forget pulleys. We're going to make pulleys more complicated. Here's the scenario I'm going to contrive. No, it's backwards. Dang it, I want that. Okay, here's what we're going to do. I'm going to take the scenario and we're going to change it. Now we're going to do this. Okay, now I'm going to sit, and if I'm blocking you, I apologize. So Brad's whole table. Move yourself to see what's going on here. Okay, this setup is the problem that we're going to look at. Before I had the things hanging off the pulley, the two FGs were in balance with each other. Now I've got a different scenario. I've got a block resting on the table, and I've got a block hanging off the edge of the table. Now it's not their force of gravity is balancing each other. What is? Yes. It's friction versus gravity. Gravity's acting down here. And the only reason this guy's not sliding is because what am I doing? I'm adding. Well, I'm applying. Sort of. My hands aren't just resting here. I'm actually actively pushing down. As I push down, if I apply a force downwards with gravity, what am I increasing on this system? I'm increasing the force of friction because I'm increasing the upward force here. If I'm pushing down, that means the desk and the thing's not falling down. That means the desk is pushing up to meet it. So that I'm increasing the force of friction by specifically increasing the normal force. Because if you look on the board, force of friction is equal to mu Fn. By pushing down, I'm increasing Fn. Whatever the mu value is between this table and this metal, it's going to be low. As soon as I let go, what do you expect to see? Gravity is going to take over, and the friction acting on this block is not going to be nearly enough to hold it back. So much so that it pulled it up over the pump. I was not expecting that. What I just did is why you weigh the masses before you use them. Because that mass took a bit of a beating. I don't know if it's actually that beating. It's totally not. Not quite so aggressively. Brad, can you get in there? Halfway down and try one. So we're just gonna. So why does this one keep moving? Oh, we're doing it. Actually, a little higher this time. Get your hand go up. Okay, so this block kept moving like inertia. But once this block was caught, there was nothing pulling this thing anymore. Friction took over and slowed the block down. So this is what we're going to analyze now. I whispered it before. We're going to analyze the comparison of friction versus gravity. Here we go. Let's analyze this system. We're going to draw the free body diagram on this. What are all of the forces acting on this system? This is effectively what I just drew, or what I just built on that desk. What forces are acting on the 6 kilogram block? Gravity is acting down. So I've got Fg, and I can put a value in there. That's going to be 6 times 9.8. We've done that math already. That's going to be 58.8 newtons. What else is acting on this block? Tension's acting up. I don't know what that value is. Just call it Ft. What's acting on this block? Kai? More Ft is acting which way on this block? To the right. What else is acting on the 8 kilogram block? Gravity is which way? Straight down. And 8 times 9.8, do I have that value in here somewhere? Where is it? I don't. What is it? 8 times 9.8. 78.4 newtons. What else is acting on this block? Oh, did we read the question? I haven't read you the question. Let me read you the question. Because Ray Reed said friction. A mass on a frictionless table. Oh, there, now we've read the question. Is there friction acting here?
No.
No. Friction shows up in example 2. A system has a force of friction of 25 newtons acting. Okay, so let's go back here for a second. But I've got a normal force, someone whispered. And that Fn is going to be the same as gravity because nothing else is acting. So the setup here is the same as what I did on the pulley, what I did with the system of blocks before. So if we're going to deal with this scenario here, which direction do we want to call positive? Or would you like me to pick it up off the pulley and redraw it the way I did before? Hands up for redraw it off the pulley. Hands up with I want to deal with the pulley as it is. You got to vote. Right now it's 2-2. There's 27 of you in this class. I have one absence today. Come on. Hands up if you want me to redraw it off the pulley. Hands up if you want me to leave it on the pulley. Okay, off the pulley it is. Here we go. Don't worry, the on the pulley people, you'll get your turn. So off the pulley, what I'm going to do is I'm going to pick this thing up, I'm going to drag it over here, and I'm just going to lift this thing sideways. So the 8 kilogram mass hasn't moved. It still has an Fg down. It still has its Fn up. It still has its Ft to the right. The only change here now is that this block up off the pulley looks like this. The Fg that was down is now acting to the right. And the Ft that was acting up is now acting to the left. This Fg was 58.8. This Fg was 78.4. And this Fn is the same as that Fg. I'm just going to leave it off for a second. Now, if you analyze it this way, it's really easy to see what's going to happen. What's going to happen to these two blocks? Ignore the pulley system for a second. If these were the forces that were acting on this two block system, what would you expect to happen? These two blocks would move to the right. Because the only forces acting in the direction of motion for these two blocks is that guy acting to the right, that guy to the left, and that guy to the right. So because this tabletop is frictionless, it doesn't matter what mass I put here. I could put 1,000,000 kilograms on this table, and if the table doesn't collapse and there's still no friction, a 6 kilogram mass would slide this thing to the right. Friction would be the only thing holding this thing back, and there's none. So which direction should we call positive in this diagram? Which way is this thing going to move? Ignore the pulley, look at this diagram. to the right would be the only thing that makes sense. If you're like, nah, I don't want to redraw this, I want to do this. It's the same analysis. There is nothing holding this block back. The only thing acting on this block that's going to start to move it is Ft. And that Ft is caused directly by this Fg. So if you're going to forget this diagram, if you're going to do this, which way should you call positive on this diagram? Clockwise on the pulley, absolutely. This way. Whether you choose to use the pulley or redraw it like this, it doesn't matter. You still have to analyze it the same way. So now we can go ahead and we can find the acceleration due to gravity. I'm going to leave that. Ooh, do I want to do that? Do I need to do that? Sure, let's do it. It's quick. F net equals ma. The only forces acting as we start at the most positive end and work back are the Fg downwards minus Ft plus Ft equals m total A, because they're accelerating together as a system. Those guys are going to cancel. I'm going to get 58.8 equals the total combined mass of 14 kilograms times the acceleration is going to give us an acceleration of 4.2 meters per second squared. I know that was quick. I'm hoping you're getting comfortable enough that I can start to speed this up for the sake of giving you more practice time in class. Does anyone need me to explain any of what I did? And if you do, don't feel bad.
Do we need to show Ft plus Ft?
Yes. I want you to show me your work. Because, Kai, it's not about you showing me your work. It's about you understanding why it is the way it is. And I'm going to start adding multiple blocks with multiple pulleys, different coefficients of friction, and and multiple ropes. And so that you've got everything organized, you know when to cross off, what you can cross off. It will never stay this simple. I could incline things, like over here. What happens when I take the same scenario and I put it on a wedge? What if I put a pulley up here with a mass hanging over? It just gets way more interesting.
The Ft would still cancel.
But if I've got multiple strings, which FTs are canceling? They are going to cancel, but I want you to, and there might be other stuff that cancels. I want you to show me that you're keeping track of it all. Tension we would solve the exact same way. Which of the blocks here makes more sense to isolate? The 6 kilogram or the 8 kilogram? Now, why the 8, Kai? Yeah, it's the only force acting. Tension is the only force acting on the 8 kilogram block. The 6 kilogram block would reintroduce a minus sign, and there's two forces acting there. So the 8 kilogram one is the better one to do. Isolate 8 kgs. If we do that, and we in the F net equals ma equation, the only force acting in the direction of motion on the 8 kilogram block is Ft. So we're going to get Ft is going to equal the mass of 8 times the acceleration of 4.2, and you're going to find that the tension in the string is equal to 33.6 newtons. Nice and easy. My last example is going to make it more interesting, because now we're going to bring in friction like Kai said we were. You're looking you were looking way less chipper than you were a second ago, Mr. Keeley. Okay, free body diagram on these, except now, I don't give you the coefficient of friction. I'm telling you what the frictional force is. It's one less calculation to do. I'm telling you the system has a friction force of 25 newtons acting on the 8 kilogram mass. So that's the first thing we could put in here. Which way is friction going to act on this system? To the left. Because the system wants to move to the right, and friction opposes motion. So force of friction has to act this way. All of the other forces are the same. I'm going to have Fg down, I'm going to have Fn up, I'm going to have Ft to the whatever direction that is, right. I'm going to have an Ft up here, and I'm going to have an Fg down here, and I can fill in all of the values because we've already calculated them. Fg here is going to be 58.8, Fg here is going to be 78.4, which means this Fn is going to be 78.4, and this force of friction here is 25. What would you expect to happen to the tension force in this problem compared to the tension we just calculated up above? Would you expect more or less tension? Or the same? You'd expect more. Because now there's a force acting back, making it harder to drag this 8 kilogram block. So let's see what we get. What's the acceleration of the masses? If this thing moves, it's going to go like this. And so that's what we're going to draw for our direction. We're going to go like this. Same thing as before. We're going to call clockwise positive. And this one I'm not going to redraw because I've done that a few times now. I'm going to work with this diagram as it is. So we're going to start with F net equals MA. And the way I'm going to continue to encourage you to do it this way is when you're putting in all of the F net forces, start at the most positive edge. So if this way is positive, this is the most positive force, and you start working your way backwards. So we're going to have this Fg positive minus this Ft because it's acting the other way, plus this Ft because it's acting in the positive direction, minus the force of friction. And these are all of the forces we need to include because this Fn and this Fg are acting perpendicular to the direction that this thing's going to slide. We only include forces in the direction of motion. And that's going to equal M total times A. And now we can go ahead and fill in these values. This Fg is this 58.8. These two tensions are going to cancel. And so now we're going to get 58.8 minus that force of friction, which you were given to be 25. If I give you the coefficient of friction, you'll have to calculate it like you did before. Force of friction is equal to mu Fn. But in this case, the value is given to you. And that's going to equal 8 plus 6 times A. So 58.8 minus 25 is going to be 33.8 equals 14A. The addition of friction should slow the acceleration down. 33.8 divided by 14 is going to be 2.4 meters per second squared. Clockwise. And clockwise means this guy's moving to the right and this guy's moving down. With the addition of friction, lower the acceleration. Makes sense, I hope. It was 4.2 with no friction. It's now 2.4 with friction. So let's go ahead and find the tension, and I'm done. To find the tension in the string, which block should I isolate? There is a best block. The 8. Why is that the best block, Kai? Because Ft is acting positive on the 8 kilogram block. Again, it doesn't actually matter which one because the value will be the same. But to avoid introducing unnecessary negatives, I'm going to pick the 8. Kai's going to pick the 8. F net equals MA. Now, we've got Ft positive minus force of friction equals MA. We can plug all this thing in now. Ft minus 25 is going to equal the mass of this block, 8 kilograms, times the acceleration of the system, 2.4. So I'm going to multiply these two together. I'm going to add the 25 over. And we're going to find that the tension in the string is now 44.2 newtons, which you guys told me it would be greater, and it is. It was 33.6. It is now 44.2. we're done. Questions, comments, concerns? Okay, cool. Here's what I want you to play with. You got 15 minutes. So much time. This is great. In a second. I would like you guys to play with the following questions. Yeah, on this page, I want you to do 1 and 2. The other ones I assigned from, the ones I didn't assign from Friday. And I want you to go back over here. Do I just assign the rest of them? I might just assign the rest of them. Let's take a look. 1's good. Let's do 3 and 4. Ooh, 5's good. 3, 4, and 5 are all similar. Make sure you very carefully draw your free body diagrams. And we'll give you 7. So I'm just leaving off 2 and 9. That's what I want you to play with. You have 15 minutes. And then tomorrow we are going to do another lab with pulleys on tables. The system that Brad and I played with is what you guys are going to do for me tomorrow. Yes, you can go get water. Yes, you can go to the washroom. You guys have another lab for me tomorrow. So get the labs you haven't done for me done, because you're getting another one.